Okay, covalent compounds part 2. Covalent compounds. And remember, we also can call these molecular compounds. That's another way of writing it, molecular compounds. And because we use that word, we usually refer to these kinds of things that form these bonds as molecules, right? Okay. So we've seen so far that when you have two different nonmetals, or two of the same nonmetals for that matter, that wish to sort of join together in some way, the old ionic giving and taking doesn't really work that well because most of the nonmetals are looking to gain electrons and nobody really wants to give any up. So instead they resort to this sharing idea, like this covalent sharing idea. And so we saw that, by using Lewis pictures, we could draw a picture of, carbon, and we could draw its 4 electrons, and then we could draw a picture of oxygen. We could put one on here and sort of one over here. And we drew the picture of oxygen. It was something like this. Say like that. And then we saw that these dots represent the outermost electrons, so 6 outer electrons for oxygen and 4 for carbon. And then it's just a matter of looking where the unpaired electrons are, like here and here. And what could happen is a sharing could occur. And it could happen twice in this case, because there are 2 places where the oxygen is looking to share. And then, of course, the carbon can also share with the other oxygen over here. Whoops, maybe I better do that this way. And it can share again here. So in this case, we have 2 shares on each side of the carbon. And so we shortened that up to a picture, a Lewis picture, using the little dashes to show those shared pairs and the electrons remaining around the oxygen like this. And so we learned to draw carbon. This particular arrangement happens to be called carbon dioxide, like this. And we're going to learn about the names today and how we call them things. But there is a bit of a problem that we don't see in the ionic compounds that we do see here. You could come up with all kinds of possible arrangements, right? Like you could double this up. You could have 2 carbons and 4 oxygens all sort of getting together. It would be a more complicated picture, and it's sort of unclear as to where all the bonds might be. But the numbers or the proportions of these atoms, I should say the proportion stays the same, but the numbers of atoms can change. So theoretically, you could have carbon with 2 oxygens, but you could also fulfill all of the sharing if you doubled everything and had C2O4, or for that matter, C4O8. And it just keeps getting bigger and bigger. Now, in reality, a lot of these combinations are not that stable. When you start packing things together, you have to remember something. Electrons are negative. So all of these little pairs of electrons here and here, okay, I'll put them here, and even these bonds, which are actually pairs of electrons, they all repel each other because of their negative charge. And if you have too many things in a molecule, all of those pushing and pulling of the electron pairs begins to create some instability. And you're going to learn more about that in your chemistry in grade 11, but for now, let's just remember that the bigger something gets, generally speaking, the more unstable it becomes, because there's just so much pushing and pulling. We're going to learn that you can still get very large molecules, very, very, very large molecules, but they sort of take on some very interesting, weird shapes because of all the pushing and pulling, and that allows these large molecules to actually do some really cool things. Their shape gives them a whole bunch of options, and that's, of course, what causes life. The molecules of living things are all very large molecules. We're going to meet some of them when we get into our next unit on biology. And these can be stable under certain conditions. But so carbon and oxygen, we don't really usually see these ones in real life. The most common one we see is this, but it's not that they're not possible. It's that if they do happen to form, they're probably very unstable and they wouldn't hold together very well. And so because of that, we have to recognize that we have many different possible combinations that can occur. And so we have to develop a system of naming that allows for all the different combinations. And so what we do instead of using, instead of what we did with the ions, which were simple, with the ionic compounds, everything was just named by the two things, and it didn't matter how many there were, right? So for example, if we had magnesium chloride, there was 2 Cls, but we didn't care. We called it magnesium chloride, just like that, because that's the only possible way that they could get together. And they always tend to get together in the lowest possible ratio. That's why we reduce things when we get crisscrosses that give us numbers that can reduce. So this was magnesium chloride, right? And then sodium chloride looks like this. It has only 1 Cl, and it's called sodium chloride. So we don't make any distinction here about the difference between having 2 or having 1 chlorine with the ionic compounds. And that's because ionic compounds are always in their lowest possible ratio. But the other compounds, these molecular compounds or covalent compounds, they don't have to follow that rule. They can get together in different arrangements, usually in the same proportions, but different numbers. So here's what we do. In order to name, let's put a little title here, naming covalent compounds. What we do now is we introduce a whole new system. We want to show what the numbers are now. It becomes important for us to determine how many of each thing is in the molecule, because it can be different, right? If you were to just say carbon oxide for this example, right? Carbon oxide, well, there's another combination that can actually work. It's called CO with only 1 oxygen. It's harder to draw the picture for that, but that can happen. Basically, that happens when the electrons get all sorts. Remember we talked about shuffling them around in some of those different orbitals, and they can do some weird stuff. So which one of those is going to be carbon oxide? Well, we have, if both of them exist, we have to give them different names. See, that never happens with sodium chloride because this is the only way sodium chloride can exist. That's the difference. So what we have to do is we have to call these different things. So we call this one over here carbon dioxide, meaning it has the one with 2 oxygens. And this one we call carbon monoxide or monooxide, sort of slurred together, which means 1, right? Mono means 1 oxygen. And that's what we have to learn. We have to learn to use a set of prefixes that will help us to count the numbers. And the prefixes we use are the common ones that you see. Mono means 1, di means 2, tri means 3. Does anybody know what 4 is? It's not quattro or quad, because that's a different language. This is Greek, I think, instead of Latin. So it's tetra. Tetra. You'll remember the game Tetris, where you had all these blocks that looked like this, different shapes, right? Sometimes it was a square like this. But if you looked closely, all of the blocks always were made of 4 pieces. 4. So tetrad, a tetrad is something made of 4 pieces. So Tetris was a game, and that's where it got its name, Tetris. So tetra is actually the prefix that we use for 4. 5 is penta. And then hexa for 6. Hepta for 7. Octo or octa is 8. And nona for 9. And deca for 10. These prefixes are probably more than enough for us to be able to name all of the possible combinations that we will see. There may be some situations where you have to use even more higher prefixes, but we don't usually see that all that often. Most of the atoms get together, it's usually 10 or less. And so these are, oh, mono. I just noticed that looks like monet. It's mono with an O on it, mono. And these are the prefixes that we use. And it's very simple, actually. The system here is much simpler because you just look at the numbers and use the appropriate symbols. Okay? So if somebody said for you that you had this compound, N2O3, what would you call it? Well, you would look at the little numbers. There are 2 nitrogens, so you would call it dinitrogen. And then there are 3 oxygens. Dinitrogen, trioxide. That's how easy it is. You just look at the numbers and use the prefixes. And remember, it's the number that hangs down on the right-hand side on the bottom that we use to count, right? To count how many there are. And that's why this one is called. Now, you could technically call this monocarbon dioxide, but we tend to ignore, just like we ignore ones when we're crisscrossing, we tend not to put the mono when it comes on the first one. So we tend to call it just carbon dioxide. And if there was one that had 2 of them, we would put dicarbon, but we just don't put the mono. It's just kind of another thing with 1, right? It's kind of obvious that it's 1. But we do put the mono on the second word, often for emphasis. So in this case, this one could technically be called monocarbon monoxide. So let me write that, monocarbon. And then when you have another vowel, right? So instead of, when you have a vowel coming up after the mono, you tend to just kind of slur it together and drop the O. So it's monoxide. Okay? So monocarbon monoxide, but we don't usually use the mono up front here because it's kind of obvious, and so it gets shortened to carbon monoxide. So the mono is sometimes used on the second word for emphasis to distinguish between these two, right? But it's hardly ever seen on the first one. It's just assumed. Let's do a few more examples. Let's say we had this one, SO2. Actually, let's go SO3. How about that? This one would be called sulfur. We don't put the mono, but trioxide. It's also possible to get SO2. This one is called sulfur dioxide. So you can see how, because there's different possible combinations, we have to use these prefixes to show the numbers. Okay? And we could do a whole bunch of them. Let's put CCl4. That would be called carbon, and there are 4 chlorines, so it would be tetrachloride. Carbon tetrachloride. Okay, we could have N5P3, let's say. So we could have, that would be called pentanitrogen. Trioxide. Right? 5 N's and 3. Oh, no, sorry. Not oxide. My mistake. Triphosphide. I got a little carried away there. Triphosphide. That's better. Notice that we still use the "ide" ending on the second word, but we have the prefixes with it to show how many there are. And then, of course, if you're doing it the opposite way, if you're going backwards, and somebody says, write the chemical formula for something like phosphorus tribromide. Let's say they give you this word? Well, you can easily write the formula by just looking at the prefixes. Phosphorus has no prefix, so it's 1. Tri-bromide means attach it to 3 bromines, just like that. So it's very easy for writing the formulas and recognizing the names, because the prefixes give everything away. And the numbers tell us which prefixes to use, right? So if you were going to do, let me think of another one here. Let's do carbon disulfide. Well, that's 1 carbon. There's no prefix. And di means 2 sulfurs. So it just looks like that. Very simple. Carbon disulfide. Okay. Dinitrogen. Pentoxide. Well, that would be dinitrogen, so that would be 2 N's, like this, and then pentoxide would mean 5 O's. So these are actually, I think, the easiest ones to work with, because it's obvious from the name which numbers to use, and it's obvious from the numbers which prefixes that you should use, as long as you remember about the mono. And, you know, every year kids ask me, if I put the mono, is it still wrong? Well, it's not necessarily wrong, but it is weird. And if you're becoming a chemist, there are things called conventions, little shortcuts or things that chemists all agree on to make their lives easier. So you don't want to be that one weird person who doesn't follow the rules, right? And it makes it harder for other people to understand you. So for the simplicity of communication, we have to sort of learn the conventions. So we don't use the mono on the first term, but we do see it on the second term sometimes. And that's really all there is for us to learn today in terms of how to name and write these compounds. And remembering that they do occur in many different ratios and combinations, whereas the ionic compounds are always the same ratio and always the same combination. It's always the lowest possible ratio as well. And that's what makes them different. Okay? All right. So we will stop there and do some practicing, and then we'll see what comes next.